Welcome to Hot Chips 32. Session 7, Machine Learning Training.
All right, hello everyone and welcome to our machine learning training session. My name is Ron, I'll be the chair for this session. Just as a quick reminder, please use the Slack channel to post questions. I'll pick from them and ask during the Q&A part. We have a great set of talks today, so let's jump right in. Our first speakers are Thomas Norrie and Nishant Patil from Google, who are going to talk about Google's training chips, TPU V2 and V3. Thomas is a hardware engineer on Google Platforms teams. He designed multiple generations of TPUs, which changed the economics of deep learning workloads. Thomas finds the interaction between hardware, software, and system to be both fascinating and a productive way to solving big and relevant problems. Nishant has a PhD in electrical engineering from Stanford. He is a software engineer on Google's system infrastructure team, and he is focused on architecture definition, co-design, and performance optimizations for multiple TPU generations. Guys, we're all super excited to hear the details, so take it away.
Hi, I'm Thomas Norrie, and I'm here to tell you about our training chips, the TPU V2 and V3. Before we get going, I just want to take a quick moment to give a heartfelt thank you to everyone on the TPU team. The only reason we're up here talking today is thanks to all the creativity and hard work of everyone involved. Working with this team to build these chips and systems has honestly been the most fun I've had in my career. There are way too many names to fit on a slide. However, thanks to Moore's Law, all that hard work does fit on a piece of silicon. Now, let's get into the details of the chip. First, a quick tour of how we got here. The year is 2014, just 2 years after AlexNet burst forth from Toronto. Deep learning is producing incredible capabilities, but we have a problem. It's just too expensive to run deep learning models as part of an internet service. The internet is chock full of useful data, and training can happen offline as needed, but serving cost scales with the number of internet users. The next year, we deploy TPU V1, our inference accelerator. Now it's feasible to serve those magical ML capabilities to our users, the ones we already take for granted like speech or image recognition. But this quickly exposes the next bottleneck, the training pipeline for all those models. So we embark on the TPU V2 project. As a result, 2 years later in 2017, the TPU V2 was powering Google services with high performance and cost-effective training. This talk will take you through how we did it. Now, as I'm sure many are aware, ML training brings unique challenges relative to inference. First, more computation. This includes the type of compute. For example, backpropagation requires matrix transposition and loss functions. But it also includes the amount of compute. An inference calculation is typically in the gigaflop scale, but training that model can require crunching an exaflop or even a zettaflop. That's about 10 orders of magnitude larger. Next, more memory. For training, data stays around much longer for use during backprop. With inference, data is more ephemeral. Wider operands. Inference can tolerate int8 numerics relatively easily, but training is much more sensitive to dynamic range due to the accumulation of small gradients. More programmability. A lot of training is experimentation, and experiments mean unstable workload targets. For example, new model architectures or optimizers. This operating mode is quite different from a heavily optimized production inference flow. Harder parallelization. For most inference, a single chip worth of compute is enough to hit key latency targets. Beyond that, chips can be scaled out. But that exaflop scale training run produces a single consistent set of parameters across the full system, and that system is quickly bottlenecked by off-chip data paths. So it's a hard problem, and more than a little daunting. As always, we had constraints, primarily time and staffing. Time matters. Each day we save during development is a day sooner we actually get to use the system. Remember, we have a bottleneck in our production pipeline, and we need to fix it quickly. And as for staffing, I know what you're thinking. Google is teeming with engineers. It's one of the largest tech companies in the world, but TPUs are just a piece. If Google were like New York City, then the TPU team would be like New York University. Sure, New York University isn't small, but no one is going to mistake New York City for a college town. So, how do we be ambitious on a budget? We have to prioritize. One way of thinking about it is asking, where must we do a great job? And then for everything else, we just have to do good enough. This slide shows where we aim to be great. Build it quickly, achieve high performance, at scale, for new workloads out of the box, all while being cost effective. And for anything not on this list, we did good enough. You'll see some examples of that. At first I was tempted to brush some of these minor embarrassments aside and pretend like this entire chip is perfect as is. But then I realized these decisions aren't actually embarrassing. In reality, building and delivering a good chip is just as much about what you decide not to do. Let's start with some familiar territory. The TPU V1, our inference chip. If you read the TPU V1 paper, this diagram should look familiar. The important part is this loop. This loop represents the high bandwidth part of the TPU. We throw data around that computation and memory loop to be crunched as quickly as possible. Model parameters feed into DDR3 above at lower bandwidth, and then on the left is host I/O at even lower bandwidth. Now, let's turn this into a training chip. First, that split on-chip SRAM space, it makes sense if I need to buffer data between sequential fixed function units, but I don't want that kind of restriction for training, so I bring it over and merge it into a single vector memory. Now, for the activation pipeline itself, let's drop the fixed functions and make it more programmable. Now, it's a vector compute unit, and let's take that matrix multiply unit and hang it off our more robust vector unit as a sort of matrix acceleration coprocessor. And now I'm looking up at that DDR3, and it's looking a bit weird. One-way parameter loading into the matrix unit doesn't really make sense for training like it did for inference. We have to write those parameters now. So let's move it over as a backstop for our memory system and transition it from DDR3 to HBM for that sweet, sweet bandwidth. We can't keep the core fed without it. Lastly, we care about scale because these are humongous computations that are much bigger than any one chip. So we connect the memory system into an interconnect fabric for multi-chip training. Ta-da! I present to you a training chip. On this next slide, I've reworked the diagram to add a bit more detail and flipped it to attach the memory system to the bottom, like a normal computer. We have the TPU Core compute in blue, HBM in green, host connectivity in purple, and the interconnect router and links in yellow. Inside the TPU Core, you can see building blocks from linear algebra, scalar, vector, and matrix compute. But that's just half the chip. Let's zoom out one step. You can see that last slide outlined on the left, and on the right is the second core. Why a second core? The simple answer is we could fit an extra one. So why not a bigger single core? Well, the latencies grow as the core gets bigger, and 2 cores per chip look to hit the right balance. The important aspect is we like fewer, bigger cores. This makes it easier to program. I can reason about one unified instruction stream operating on big chunks of data, rather than trying to lash together lots of tiny cores. This is a big data problem, so we took advantage of it. Let's first dive into the compute. This core was co-designed closely with the XLA compiler team to ensure programmability. In these discussions, we landed on 2 important themes. First, the VLIW architecture would allow us to utilize known compiler techniques, and second, we can ensure generality by architecting within the principled language of linear algebra. Now, let's dive the next layer deeper. The scalar unit is where computation originates. It fetches the complete VLIW bundles from a local instruction memory, executes the scalar slots locally, and then forwards decoded instructions onto the vector and matrix units. The VLIW bundle itself is 322 bits and is composed of 2 scalar slots, 4 vector slots, 2 used for vector load store, 2 matrix slots, a push and a pop, which I'll touch on later, 1 miscellaneous slot, like a good old delay instruction, and 6 immediates. Here's the diagram version. At the top left is the instruction bundle memory. While an iCache would be nice, we kicked it old school and made it a DMA target for software-managed instruction overlays. Not the flashiest, but remember, this part just needs to be good enough. The greatness comes elsewhere. Coming down the left, we do scalar decode and issue. On the right is where the scalar execution happens. Up from the bottom is the DMA port into the memory system, primarily to HBM. That feeds into local scalar SRAM that we can issue loads and stores against. This feeds into a 32-deep register file containing 32-bit words, and finally into a dual issue ALU. Execution interlocked is managed by standard hold conditions on the instructions, as well as sync flags to interlock against software-managed DMA operations. Following the instruction bundle down to the vector unit, we now zoom into a single vector lane. The whole vector unit is 128 instances of this slide. Within each lane, there's another 8-way execution dimension that we call the sublane. Each sublane contains a dual-issue 32-bit ALU connected into a 32-deep register file. So the vector compute unit in total lets you operate on 8 sets of 128 wide vectors per cycle. The register files perform loads and stores against the lane slice of vector memory, and that memory connects into the DMA system, primarily providing access to HBM. But what's all that on the right? This is the connectivity into the matrix units. We use the push instruction slots to send data vectors out to the matrix units. Returning result vectors land in something we've called the result FIFO. This is a small staging buffer for results, and it's accessed using the pop instruction slot. This lets us decouple the execution schedule for the long latency matrix operations and shorten the register allocation windows. Now, let's follow those wires to the matrix multiply unit, the computational heart of the TPU. This is a 128 by 128 systolic array of multipliers and adders, giving us 32,000 operations per cycle. The inputs are two matrices, a left-hand side matrix and a right-hand side matrix. The left-hand side matrix streams over the preloaded right-hand side matrix to create a streaming result matrix that is sent back to the vector unit's result FIFO. And as noted, the right-hand side matrix can be optionally transposed on the loading route. Critically, this systolic array structure gives us very high computational density. While it contains most of the flops, it's not the most significant contributor to chip area, as you'll see later. One other important aspect of the compute density comes from the numerics. The multiplications are performed in bfloat16. This is a 16-bit format that has the same exponent range as float32, but with fewer bits of mantissa. However, the accumulation happens in full 32-bit floating point. What's great about this mix is it works seamlessly for almost all machine learning training, all while bringing a significant hardware cost benefit. And hardware savings are real money savings. We found this winning combination through a variety of early design experiments, and that's why the TPU V2 is the original bfloat16 hardware. One obvious question is, why 128 by 128? This graph gives some intuition. Matrix unit operations grow in proportion to the area, but the operand I/O grows in proportion to the perimeter. So as you can see with the red line, a single bigger unit provides more top-line flops per operand when compared with more matrix units of smaller size, even at constant flops. But the blue line shows an example utilization trade-off encountered when the workload doesn't fit quite right into that tile size. As you can see, we get good utilization improvement moving from 256 to 128, but the advantages taper off after that. Combining this with the favorable compute versus wire density ratios, 128 by 128 hits a nice sweet spot where we can get good utilization without devoting too much area to wiring. Lastly, we have one more set of units that provides efficient execution of common matrix operations, transposes, row reductions, or column permutations. So that's the core in a nutshell. Now onto the memory system. How do we keep all that compute fed? As noted earlier, the TPU Core has a variety of SRAM-based scratchpad memories. These are architecturally visible to software and accessed using loads and stores. This approach gives the compiler predictable execution control over both compute and SRAM. But the memory story can't stop with SRAM. SRAM is small compared to the datasets and models we want to work with, so we back it up with high bandwidth in-package HBM. The compiler moves data between HBM and SRAM using asynchronous DMAs. When a DMA finishes, a completion notification lands in a core sync flag, allowing the compiler to stall until data arrives. So in blue, we have predictable, tightly scheduled execution, and in green, we have background DMAs prefetching from the larger HBM space, and the handoff between the two is managed with sync flags. HBM itself stores vectors and matrices. To reduce DMA descriptor overhead, we allow DMAs to describe strides through memory so that we can slice off subdimensions of larger dimensional structures. And let's not forget what that HBM is really giving us at the end of the day. Bandwidth. At 700 gigabytes per second per chip, that's 20 times more than what we had with DDR3 and TPU V1. This bandwidth allows us to extract full compute utilization at much lower data reuse rates. Zooming out to the chip-level memory system, you can see our two cores each connected to half of the chip's HBM. Each core has a set of PCIe queues for moving data to and from the host, and between the two cores is the interconnect router, which also connects to the off-chip links. But why split the memory space on the same die and require the two cores to communicate over the interconnect? That goes back to our number one goal: build it quickly. It was easier. Now, let me give you an intuitive sense for bandwidth with proportional line widths. What immediately sticks out is that PCIe straw is tiny, the in-package bandwidth is huge, and the interconnect links are somewhere in the middle. And so it's critical for performance that the TPU is flexible and programmable enough to operate on all data locally without regularly moving data back through the host. Next, let's dive into the interconnect. You can see we have 4 off-chip links, each delivering 500 gigabits per second. These 4 links are designed to be connected into a 2D torus, which works great for many common ML communication patterns like all reduce. An important property of the interconnect design is ease of use. DMAs to other chips look just like DMAs to local HBM, albeit with a push-only restriction for simplicity. This common DMA interface allows the compiler to treat the full system's memory space in a consistent way. And the final slide for TPU V2, the basic floor plan. I'll admit, it's not the most stylish, but it got the job done so we could focus on more important things. For the color scheme, I've stayed consistent with the prior slides. You can see that we devote most area to the compute cores in blue, both noticeable area to the memory system and interconnect as well. The 2 cores are split across the top and bottom, and the interconnect router lives in the donut hole. The white areas are not empty, but filled with wiring. I'd like to draw your attention to the size of that matrix multiply unit, one in the top center and one in the bottom center. This demonstrates the point earlier that the bfloat16 systolic array gives us a lot of compute density. Whew, we made it. That was TPU V2. Let's see if we can get through TPU V3 in just a few more minutes. Our approach with TPU v3 was to explicitly avoid the second system effect. We didn't want to blow everything we worked hard for in v2 by building the kitchen sink into v3. We took an approach that leveraged what we already built, but let us pick up the low-hanging fruit we left behind from going fast. Let me show you what I mean. Here's the TPU v2 slide from earlier. Let's turn into a v3. We double up the matrix multiply units. That's 2x max flops right there. And as you saw, they're not too big, so this is high leverage. We bump the clock frequency from 700 to 940 megahertz. That's 30% we get by tuning pipelines. We bump HBM performance by 30% using a higher bus speed and double the capacity, enabling bigger models. But no need to stop there. We bump interconnect link bandwidth by 30%, taking us to 650 gigabits per second per link. And lastly, we added support for a larger system. It feels a bit quaint now, but at the time, we thought the 256-chip V2 system was pretty big. Well, machine learning apparently has a voracious appetite for scale, and so we moved to 1,000-chip V3 systems. Now, we did plenty of other things as well, but honestly, that's all below the fold stuff. What I showed you are the changes that mattered most, and it let us over double performance compared to V2. I'd like to cap this section by going back to our key goals. How'd we do? We did great. We built it quickly thanks to our cross-team co-design philosophy. We found simpler to design hardware solutions that also gave us more predictable software control. And along the way, we were willing to make difficult trade-offs for schedule. We achieved high performance thanks to that matrix compute density, HBM bandwidth, and XLA compiler optimizations. We support scale natively with our system-first approach and simple-to-use interconnect. To support the deluge of training workloads, we built a big core grounded in linear algebra that works well with the XLA compiler. And HBM ensures we have enough capacity to keep up with growing models. And lastly, we did it cost effectively. Those matrix units are efficient. The design was simple without gratuitous bells and whistles, and we ensured we got our money's worth with performance. So there you go. That's how we did it. But not so fast. This is just the chip. What we really build are systems, and what we really care about are how those systems perform. So next up, Nishant will walk you through the system design and performance.
Thanks, Thomas. Hi, I am Nishant Patil, one of the members of the TPU team, and now I will talk about the system architecture and performance of training TPUs. A key feature of the training TPUs is the ML supercomputer design with dedicated interconnect. TPU v1 was a single-chip system built as a coprocessor to the CPU. This worked very well for inference. However, for training, we have very large data sets, and training Google production models would require several weeks or months to train on a single chip. Hence, TPU v2 and v3 were designed to be networked from the start. This required the design of an ML supercomputer with multiple chips working in conjunction to train a single model. Here is a high-level diagram of the training pod architecture. We have each individual TPU chip interconnected with 4 other chips to form a 2D torus network. Some of these torus links are within the TPU board, and the rest are through cables across trays and racks. This network is critical for achieving scalable synchronous training across TPUs. Asynchronous training was the state of the art when we started building the system, but our study showed that synchronous training would perform better, and actually it does converge better. Async training was primarily useful for broader scaling with more limited networking. We then connect this TPU pod to storage over the data center network to feed the input data for the model through PCI-connected CPU host as shown here. The system balance across CPU, network, and storage is critical to achieve end-to-end performance at scale. 64 of these TPU v2 boards, each with 4 chips, are connected to form the TPU v2 supercomputer. For TPU v3, we connect 256 of these boards to form the 1024-chip supercomputer. The TPU v2 pod has over 11 petaflops of compute and 4 terabytes of HBM across 256 chips. TPU v3 has over 100 petaflops of compute with 32 terabytes of HBM. Now let's see how this ML supercomputer performs for Google production workloads. We analyzed 6 internal applications across 3 model categories. The first category is the multilayer perceptron with embeddings, which is labeled as MLP. One of these is a variant of the published rank brain. We use 2 CNN networks. CNN0 is AlphaZero, while CNN1 is an internal Google model for image recognition based on inception. We also have 2 recurrent neural network models for translation and speech applications. Now comparing the speedups at scale, MLP0 and MLP1 show 40% and 14% of perfect linear speedup at the 1024 chip scale. For these MLP applications, the speedup is limited by distributed embedding computation across the TPU pods. With CNNs and RNNs, we see that we achieve nearly ideal scale-up across 1024 chips. This amazing scaling across workloads is due to the dedicated TPU interconnect, which is much easier to optimize against since it's dedicated with predictable performance at high bandwidth and tight late latencies. The previous analysis was a snapshot of the state of the production applications at a given point in time. However, these production applications are being constantly updated and improved. For example, the next version of MLP, which is called here MLP0 Next, has increased size for better quality. Combined with software improvements for improved embedding performance at scale and the larger model size, the scalability of this production application has improved from 40% to 67% at the 6024 chip scale. Now let's compare the performance across the generation of TPUs. As Thomas mentioned, the peak performance of TPU v3 is around 2.7x that of TPU v2. However, the memory bandwidth only improved by 30%. Across both production applications and MLPerf benchmarks, the performance improvements compared to the TPUs is significantly higher than the memory bandwidth improvements across generations, suggesting that the increased compute added in TPU v3 was very useful for many applications. One aspect I want to highlight is the software stack and performance gains mature over time. Here is a graph that shows the performance improvements over time between MLPerf 0.5 and 0.6 benchmarks. We see similar gains for production applications. For example, CNN0 improved by 1.8x through improved use of lower precision filtering point and optimized model architecture. MLP0 improved by 1.6x based on improved partitioning and placement of embeddings and XLA optimizations. In practice, these performance gains have been used to enable larger and more complex models for better accuracy. As another comparison, TPU v2 and v3 also do very well on inference. Here is a comparison of a production translation application discussed in the TPU v1 paper. TPU v1 paper described increasing the memory bandwidth of the TPU to improve inference performance. With TPU v2, we have significantly more memory bandwidth, and the same production application for LSTMs runs more than 5 times faster with TPU v2 with 3x reduction in latency. This lower latency allows for larger batch sizes while still meeting the latency targets, and also the larger batch sizes allow production to be served. As another comparison, TPU v2 and v3 also do well on inference. Here is a comparison of a production translator application, LSTM0, as discussed in the TPU v1 paper. The TPU v1 paper described increasing the memory bandwidth to improve the performance for inference. With TPU v2, we have significantly more memory bandwidth, and the LSTM application runs more than 5 times faster on TPU v2 compared to TPU v1, with 3 times reduced response time. The lower latency allowed for larger batches in production, yet still meet the latency targets. With these larger batches, the throughput was further improved by more than 10x compared to TPU v1, with a 2x reduction in latency. Now, if you move to TPU v3, the same application has a reduced latency by more than 30%. In summary, TPU supercomputers efficiently run production applications at scale. TPUs are widely used within Google to accelerate both production applications and also extend research frontiers. We built our TPU systems with collaborative co-design specifically for this purpose. After years of production experience, TPUs have proven the value of this approach. As deep learning continues to evolve and we understand the workloads and scaling limits better, there continues to be many opportunities for further co-design for the next generation of TPUs and other domain-specific architectures. This work was a large collaboration with our colleagues at Google, and we are honored to be able to present on their behalf. Thank you for listening, and we hope you enjoyed learning about TPUs.
Nishant, Thomas, thanks much. This is great information. The audience is asking tons of questions, so I'll start with picking a few. So availability-wise, with a few TPU v4 results submitted to MLPerf, do you have a roadmap on when this will become available on GCP?
We don't currently have a roadmap for the TPU v4 right now. Right now, we're enjoying using it internally, but I'm sure we'll have more details later.
All right, thanks. Now we have a couple of questions on recommenders. Anirban is asking, how do you deal with large embedding tables, several hundreds of gigabytes, that are quite common in recommender systems?
Yeah, so we partition those tables across the multiple TPU chips because one single chip cannot fit the tables, and then we use the fast ICI network to actually communicate between the chips, the tables, and the gradients.
Thanks, Nishant. And a related question, are there chip-level architectural features that are there to help MLP and recommender systems?
Yeah, I think, oh, go for it, Nishant.
No, go ahead. No problems.
All right, I'll take it. Yeah, actually, I do think there are a lot of interesting opportunities in the space, and it's definitely a complex set of models to optimize for. As you note, as Nishant noted, you're sharding these giant tables across the interconnect, and so that's why that interconnect bandwidth can be very critical. Scatters and gathers and things like that become very important. So we have various techniques we try to use internally on the TPUs to make this stuff run well.
All right, the next set of questions is on scaling. So what are the trade-offs that you see between point-to-point topologies like the two-dimensional torus and the switch-based topology like NVIDIA showed with the A100?
Yeah, it's a good question. I would say I think both are valid at the end of the day. I think there are a lot of different types of systems you can build. I think direct or indirect networks, they each have trade-offs. One of the nice things, one of the biggest advantages for us in using the direct topology with the torus was we didn't have to go build an extra switch chip. We don't have to manage an extra networking plane and things like that. It's all built in. You amortize some of the costs being in the same package and things like that.
Yeah, and I think scaling up to large systems and the network traffic patterns do work well for the torus links that we have.
All right. And another question, would you be able to share the protocol used through the interconnect that you built across TPUs?
It's simple, I guess is what I'd say. Nothing too complex. We went for simple and fast and really high bandwidth. And so the nice thing about high bandwidth is you don't have to do anything too fancy except get out of the way there. It is a custom protocol internally. We don't have further details at this time, though.
All right, and I'll go for a last question that is kind of with the similar direction of your talk. Given the benefits that you get from every TPU generation, do you trade off between time to market and more features, and how do you do so?
Yeah, definitely. That is the biggest constraint, really, I'd say. You have to do a good job there. We have a lot of ways of prioritizing what we think is important and finding the right cut point. As you note from the talk, it's really important not to go too far, but if you don't go far enough, you don't really recover that value. And so internally, it's a lot of analysis. You can't beat human thought and intuition and teams working together. And I don't know, Nishant probably wants to add some more too. He specifically works on that.
Yeah, I think also like the field is changing very rapidly. So I think we keep on trying to get abreast of whatever latest features need to be added. But obviously we have generational, we can add it in the next generation if needed.
All right, guys, I enjoyed it a lot. The audience did as well. Thank you very much for your time.
Yeah, thanks, you too. It was fun.
Thank you. Bye.
All right, our next speaker is Sean Lee from Cerebras. Sean is a computer architect who has worked on a variety of technologies, including transactional memory, high-performance CPUs, networking and storage, and large-scale server clusters. He's the co-founder and chief hardware architect for Cerebras, and he's going to talk about software-hardware co-design for the Wafer-Scale engine. Sean, the floor is yours.
Hi, I'm Sean, co-founder and chief hardware architect at Cerebras Systems. At Cerebras, our mission is to drastically change the landscape of compute for AI. And that requires revolutionary new hardware and software, both co-designed to solve the most challenging deep learning problems of today and beyond. This is our chip, the Wafer-Scale engine. It's the largest chip ever built using a single piece of silicon. It's over 46,000 square millimeters in size and contains 1.2 trillion transistors, all powering 400,000 AI-optimized cores. And the Wafer-Scale engine is the heart of the Cerebras CS1 system. The CS1 is a full solution in a single system where every detail is designed for the unique needs of the Wafer-Scale chip. But it's still easy to use because it's still programmed using standard ML frameworks like TensorFlow and PyTorch and installs in a standard data center rack. We have many systems already delivered, installed, and in use today at our customers. The Cerebras CS1, coupled with the Wafer-Scale engine, has been built from ground up for this type of work, making it today's most powerful AI computer. And that's because each of the 400,000 cores is designed to be optimized for deep learning. First, the central component of any core is the compute. And our core is fine-grained, fully independent, and programmable. It has hardware data flow mechanisms to enable dynamic execution and sparsity acceleration. This makes it ideal for the changing neural network field and increasingly dynamic neural network architectures. The second key component to any architecture is memory. The memory is all fully distributed on-chip SRAM local to the cores. This avoids the bandwidth and latency bottlenecks of traditional off-chip memory and enables higher utilization and smaller batch size than what's possible with traditional memory architectures. And finally, it is critical for a deep learning optimized architecture to have a high bandwidth and low latency interconnect. The fabric on the wafer is a 2D mesh optimized for the local communication of neural networks. It spans across the entire wafer with the same performance everywhere. That's only possible because of wafer-scale integration, because all the cores are connected on chip, on silicon, no wires. This is the high-performance fabric that enables all 400,000 cores to operate as a single massive chip to solve a single neural network problem. When you bring all of this together, you get linear performance scaling because it's a single chip. And across all of these cores, it delivers orders of magnitude higher performance and efficiency. That's cluster scale performance on a single chip. But all of these performance gains can only be realized if you have software that can take advantage of the new and unique architecture. At Cerebras, we co-designed our software for scale from the very beginning. And today, I'm going to cover how our co-designed software leverages the unique capabilities of the first Wafer-Scale engine, and maybe a sneak peek at what's next. The Cerebras graph compiler software takes the user workload from the framework and generates the executable that runs on the wafer. And there are 5 key steps to this process. We start with an input description of the neural network from the ML framework such as TensorFlow or PyTorch. We then extract the compute graph and we create an internal representation of the workload. The next step is to match that graph to our kernel library. That's what implements the individual computations of the graph. Then we take the kernels and we place and we route them on the fabric of the wafer. And then finally, we create an executable image which programs the wafer, making it ready to train the neural network. With this flow, we enable straightforward programming while maintaining flexibility and high performance. Next, I'm going to describe these steps in more detail. The central component of the Cerebras graph compiler is the kernel library. Every neural network graph is composed of many kernels, each one performing an operation used within the neural network. Cerebras kernels are all expressed in our intermediate representation as general nested for loops. On the right, you can see an example of the matrix vector multiply kernel. By using a nested for loop representation, instead of explicit named ops, we get maximum flexibility. The for loop representation, it covers all operations used today and new operations of tomorrow without having to constantly update our IR for new ops. Now, once we've identified the kernel, we need to implement the operation on the underlying compute fabric. And there are two ways kernels are implemented. First, kernels are auto-generated using polyhedral compiler techniques. This is actually a key reason why we use nested for loops for our representation. It allows us to use polyhedral loop analysis to determine how to unroll these loops both in time and in space across the fabric. On the right is an example of how we map the matrix vector multiply for loops to the fabric. Using automatic code generation, we can cover the full spectrum of operations, but sometimes it's still not sufficient to get the absolute highest performance. And so we also support a second way of implementing kernels, and that's manual hand-optimized kernels. We use this for the most common kernels that have the maximum impact on network-level performance. Here we use highly optimized, handwritten kernels that are tuned to take advantage of every microarchitecture capability. And these hand-optimized kernels, they live side by side with the auto-generated kernels, and the remainder of the stack uses them interchangeably. By using a combination of auto-generated and hand-optimized kernels, the Cerebras compiler stack enables both full generalizability and high performance. Once we've matched to a set of kernels, the next step is to determine the best strategy to map these kernels to the fabric. And there are two high-level options that are explored algorithmically: model parallel and data parallel. Within model parallelism, the stack determines the optimal size of independent kernels to run in parallel. Within data parallelism, the stack determines the optimal number of times to replicate a single kernel to run in parallel. And all of this is formulated as an optimization problem to find the best balance of compute, memory, and fabric resources for every kernel. The wafer has 400,000 cores, so there's a lot of freedom to find the optimal solution. And that's where kernels are sized, taking into account their resource demands and the impact on the network level performance. Kernels that need more resources are given more area on the fabric. But there's a fixed amount of area and there's a fixed amount of resource. So increasing one kernel necessarily requires decreasing another. For the neural network shown, these two example resource allocations will produce vastly different performance characteristics. As an example, the allocation on the right, it has higher performance because it allocated more resources to the blue kernel, which was a bottleneck in this example. Here is an example of all the options we have when sizing an individual kernel within a neural network. All kernels are parameterizable, so they can be resized without impact to their functionality. In fact, all of these options that are shown here, they're all functionally identical, and they perform exactly the same operation within the kernel. Kernels can be resized by stretching them across more cores, or by using replication through data parallelism, or a combination of both. For example, let's consider the option in the middle as a baseline. This is sized using 6x6 or 36 cores. We can increase that to 12x12 for 4x more area and 4x higher performance. Or we can decrease it down to 3x3 for 4x less area and 4x lower performance. And additionally, both height and width are parameters within the search space also. So that means we can get non-squared aspect ratios as well. And that's important because in addition to sizing these kernels, we also need to pack and fit these kernels into the 2D fabric of the wafer. And that's done through placement and routing. This is a process actually very similar to floor planning in EDA tools. Each kernel of the neural network is placed on a spatial region of the fabric. And by placing the kernels on independent regions of the fabric, the stack natively supports model parallelism for performance. These kernels are then connected to each other through fabric routing. And this entire sizing and mapping is solved as a multivariable global optimization problem where the objective function is to maximize throughput and maximize utilization. And finally, when complete, we get an executable that runs on the wafer that trains a neural network based on the input training data. The end result of this co-design approach is a high degree of flexibility and performance. And it provides three key benefits. First, the software stack natively supports both model parallel and data parallel execution, producing the optimal mapping for the specific needs of every neural network. Second, it's capable of harvesting sparsity, both native sparsity already present in neural networks and inducing additional sparsity for even more performance. And third, it's capable of fine-grained dynamic execution. This enables new and novel neural network architectures. Next, I'll dive into each of these in more detail. The primary way the Wafer-Scale engine achieves performance is through parallelism. We have 400,000 cores after all, so we can do a lot in parallel. But there are different forms of parallelism. On one axis of the spectrum is data parallel. Here we run multiple samples at the same time on replicas of the neural network. On the other axis of the spectrum is model parallel. Here we run multiple parts of the neural network at the same time on different sections of the fabric. And it's important to note that this is in fact a spectrum, and these forms of parallelism, they can be mixed, and different points on the spectrum have different training characteristics. By supporting both forms of parallelism natively within the software, we give full flexibility to choose what fits the neural network the best. To scale relatively large networks, we use model parallelism. This is done by running different layers on different sections of the fabric where all layers are running at the same time. And this is only possible at this scale because of the high bandwidth and low latency interconnect of the wafer. There's enough performance for the kernels to be sized without having to consider traditional device boundaries. A single kernel, it can be split across the equivalent of multiple GPUs without performance loss. And there's enough fabric performance to connect everything together at scale. Doing this on a traditional GPU is difficult and often impossible because of the limited I/O between GPUs and between servers in the cluster. A key advantage of model parallelism on the Wafer-Scale engine is small batch size. Since there's only a single instance of a neural network running, we don't need to increase the batch for replicas of the network. And similarly, since there's only a single instance of the network, there's no weight synchronization overhead at all. On the right is an example of a 4-layer BERT network scaling linearly from a quarter of the wafer all the way to 400,000 cores. And it's all done at a fixed batch size of just 16. So you can see model parallelism at wafer scale gives linear cluster scale performance with small batch size, which is simply impossible on traditional clusters. For smaller networks, we use data parallelism to run replicas of the network in parallel. This applies to networks that can't be directly stretched to the entire wafer through model parallelism. However, data parallelism at wafer scale doesn't necessarily imply the large batch size like it does in traditional clusters. And that's because the memory architecture enables each replica to run at very small batch size, essentially one sample at a time or just batch size of 1. By using data parallelism, we are replicating the kernel, so we can't avoid weight synchronization. But the overhead is minimized because of the low latency and high bandwidth interconnect. On the right is an example of various levels of data parallelism applied to the BERT attention kernel. Each line is a different number of replicas. And as you can see, for this particular kernel, with a single replica, it's reached the native scaling limit at about 100,000 cores. So giving more cores doesn't give higher performance for a single replica. But by deploying just a modest number of replicas, which is just 8 in this case, we can scale linearly all the way to 400,000 cores. So data parallelism at wafer scale gives linear performance scaling for smaller networks with only a moderate batch size, and that's also not possible with traditional clusters. Beyond parallelism, the second benefit of co-design is sparsity acceleration. Neural networks are naturally sparse. This means there's a lot of zeros in the computation, and the main operation in neural networks is a multiply add. And we all know multiply add by 0 doesn't change the result at all. So if we optimized our core and our kernels to run the dense neural network on the left, but it really looked like the sparse network on the right, that would be incredibly wasteful. So our compute core has native sparsity processing directly in the hardware. And this is achieved through data flow scheduling where compute is triggered by data. The fabric transports both data and associated control in the hardware. And once the core receives that data, it triggers the tensor instruction to execute on the data path. This data flow scheduling enables intrinsic sparsity harvesting. And that's because the kernel that sends the data filters out all zeros. Since all compute is triggered by data, if the sender doesn't send any data, the receiver doesn't perform any compute. It's that simple. Not only do we save power because we're not performing the wasted work, but we also get acceleration by skipping to the next useful work. And by using a large number of these small cores with fine-grained data paths, we can maximize the utilization for dynamic, non-uniform work. To the end user, not only does this enable higher performance for naturally occurring sparsity, but it enables the user to explore sparse ML methods that are not practical on GPUs today. Here's an example of naturally occurring sparsity in the transformer network. As you can see on the right, the transformer network has a feed-forward block that's in both the encoder and the decoder. This feed-forward block uses both ReLU and dropout. These are both common ML techniques that create natural sparsity. In the case of transformer, the output of ReLU is almost entirely sparse, with up to 90% naturally occurring sparsity. The dropout is about 30% sparse. With this naturally occurring sparsity, our kernels running on our data flow cores achieves a 1.2x higher performance with no changes to the network. However, the natural question is, what if there's no natural sparsity? Can we still get acceleration? And the answer is yes. We can induce sparsity into neural networks relatively easily. This can be done by simply using nonlinears like ReLU instead of dense nonlinears, or by using techniques to force sparsity like simply dropping small magnitude values. On the right is a 34-layer, fully dense, fully connected network that we created to illustrate this property. The leftmost columns show a baseline where there's no sparsity. Now, just by adding ReLUs after every layer, we can achieve 1.7x higher performance with the naturally occurring sparsity from ReLU. And additionally, if we drop 50% of the activations, we can achieve up to 2.4x higher performance. Now, admittedly, this is somewhat of a synthetic network, but it turns out that this applies to real neural networks as well. Let's look at the BERT network as an example. BERT has no naturally occurring sparsity at all, but we can induce sparsity on most layers in both the forward pass and the backward pass. As you can see on the right, the more sparsity that we induce, the higher the performance. For BERT, we can achieve up to 1.5x higher performance with roughly 50% induced sparsity and minimal accuracy loss. Ultimately, the ML user has full control over these techniques, enabling them to explore sparse ML methods that are not practical on traditional processors today. And lastly, The third benefit that co-design uniquely enables is the ability to run smarter, more dynamic ML techniques at very high performance. The data flow architecture enables dynamic execution, and we've already seen how that benefits sparsity. But this flexibility also enables other forms of dynamic execution also, such as independent token-by-token processing. The Wafer-Scale engine is a MIMD architecture. That's multiple instruction, multiple data. All of the small cores are independent, so we can run different operations on different data at very fine granularity. And it's this fine-grained dynamic execution that unlocks many novel ML techniques. And here are a few examples. The first is true variable sequence length support. This means we can stream tokens one at a time and stop processing at the end of the sequence. So there's no need for any wasted compute on padding. The second is higher utilization for irregular models. Some of the best performing models today are created using methods like neural architecture search. And this often results in highly irregular and non-square matrices. And these are hard for traditional architectures to run efficiently. But because our cores are processing data at a very fine granularity, these irregular networks don't suffer utilization loss and can be run at full performance. The third example is dynamic depth networks. These are models where the depth of the network changes based on data. The universal transformer network on the right is such an example. Here you run only enough layers to achieve an objective and then you stop. With our fine-grained dynamic execution, we can run a dynamic number of layers for every sample. And the fourth is dynamic and longer sequence length. This uses the same dynamic early stopping mechanism, but on the sequence length dimension, where you process only enough of the sequence to achieve an objective, and then you stop. Imagine being able to process sequences that are orders of magnitude longer than they are today. This could enable things like understanding an entire paper by just reading the abstract, for example. Now, these are just some of the potential dynamic ML methods enabled by the flexibility of fine-grained dynamic execution. This gives the ML engineer the ability to efficiently explore ML techniques beyond what's possible today. Everything I've talked about today, from flexible parallelism to sparsity to new ML techniques, is only possible because of tight hardware-software co-design. It's only through co-design that we can achieve the smarter and larger models demanded by the ML community. That's what makes the Cerebras CS1 the world's most powerful AI computer. The automatic ability to use both model and data parallelism allows it to optimally accelerate every unique workload. The fact that it's a single chip in a single powerful node allows the CS1 to not just provide performance, but accessible cluster scale performance to enable easier and more efficient scaling of extremely large networks. By providing flexible and dynamic execution at scale, it enables today's models to run faster and more efficiently with sparsity harvesting. And it unlocks tomorrow's models to use smarter ML techniques with full performance. Flexible parallelism, flexible execution. These are the software techniques that allow us to take full advantage of all 400,000 cores in the Wafer-Scale engine. So now, imagine what all this would look like on 850,000 cores. Perhaps it looks something like this. This is the second generation Wafer-Scale engine. It has 850,000 AI optimized cores. It contains 2.6 trillion transistors. It's fabbed in partnership with TSMC on their 7 nanometer process. And we have it working in our lab today. Imagine this coupled with the power of software that was co-designed from the very beginning for scale. How vastly can we accelerate today's AI workloads? And what new AI workloads might we unlock with this scale of flexible performance? Stay tuned for more information in the coming months. Thank you very much.
Sean, thank you very much. As always, fascinating. The numbers are mind-boggling. There are tons of questions in the Slack channel, so let's start with the first one. Given that GPUs and TPUs report near linear scaling, what would you say is the main benefit of a wafer-scale engine?
That's a good question. I think, GPUs and TPUs see linear scaling in some workloads. And actually, as I think Ron mentioned in his keynote earlier today, what we end up seeing, I think, is that often the workload gravitates to the hardware, right? And so when the hardware that you have at your that's available to you is a Scalar architecture with many relatively small chips connected together with relatively low performance I/O, you have to look for workloads that can scale effectively. But as you can see with the Wafer-Scale architecture, we can open the opportunity to a lot of novel ML techniques that couldn't be explored efficiently, such as some of these dynamic models that I alluded to at the end. These are just models that would not be able to run on traditional hardware, where traditional, extreme data parallel scaling just wouldn't apply. And so I think that we are ultimately at the very beginning, I think, of a new age of new computer architecture for deep learning, and being able to provide these very fine-grained dynamic mechanisms to the ML user, we believe will provide the kind of compute substrate to enable a lot of new novel techniques that today aren't available.
All right. There are a few questions on how can you feed that enormous beast? How the PCI won't hold, right? So what do you do?
That's a really great question. Obviously, when you increase the amount of compute of the accelerator to the level that we have, in a traditional server where the bottleneck might be your GPU or your TPU, it moves, and of course I/O is the next bottleneck. And so this is part of the reason why at Cerebras we are a system company. Our product is the full appliance, it's the full system. And it's because we need to be able to control all of the aspects of the end-to-end solution. And on the question of I/O in particular, we've designed a 1.2 terabit per second Ethernet interconnect to be able to feed the Wafer-Scale engine so that it can keep up with all the compute that's on the wafer.
All right. There are a few questions on, given that you have 400,000 cores, how long does it take to compile a model to the Wafer-Scale engine?
That's a really great question. Ultimately, the process of compiling, as I mentioned in the talk, is a relatively algorithmically complex problem, which is solved as an optimization problem. And so, solving it brute force is not possible. However, using techniques like annealing and heuristics, you're able to get the compile times down to a very reasonable range. And we absolutely are borrowing many ideas from the EDA industry that have iterated on these algorithms over the past several decades. And when you compare the problem that we're solving versus a traditional EDA problem, we are solving a problem that is arguably significant, orders of magnitude easier, in the sense that even though we're placing on 400,000 cores, we're actually placing and routing a much smaller number, maybe hundreds or thousands of elements. And when you compare that with the size of problems that these types of algorithms were designed for, which could perform placement and routing on millions or perhaps even billions of elements, our problem is much simpler. And so when it all comes down to it, we get compile times in the minutes for very typical, even very large networks.
All right, nice. Last one for today. The audience is interested about how much SRAM do you have in the second generation engine? Could you share that?
That's a great question. Unfortunately, today we're not sharing much more beyond what I've just shared. As you can probably tell, even from the picture, we just got the chip into our lab. That picture is just a photo one of our engineers took in the lab, and so we will be sharing much more in the coming months.
All right, Sean, thank you very much. Fascinating stuff. Thanks for taking the time.
Thank you very much, Ron.
All right, with that, we're going to our last talk in the session. The two speakers are coming from ETH Zurich. Florian and Fabian designed Manticore, a 4096 core RISC-V architecture for floating point computing. Florian received his B-Science degree from TU Vienna and his M-Science degree from Swiss Federal Institute of Technology. Fabian received his B-Science and M-Science from ETH Zurich. Both of them, Florian and Fabian, are currently pursuing their PhD degree with the Digital Circuits and System Group of Luca Benini in ETH Zurich. Their research interests include high-performance computing, design of VLSI circuits, and near-memory processing. So with that, let's hear about the Manticore.
Welcome to our presentation about Manticore, a 4096 RISC-V chiplet concept architecture for ultra-efficient floating-point computing. My name is Florian, and with me is Fabian. We are both PhD students from ETH Zurich, sharing an office and the presentation today. So let's start by asking ourselves, why do we even care about medium to high precision energy efficient floating point computation? Advancements in domains such as data analytics, machine learning, and scientific computing are directly coupled to the available compute resources, and the demand for them is ever growing. Increasing node densities make it ever more important to make the designs energy efficient, as thermal design power effectively limits the amount of active compute units. While many emerging architectures, especially in the machine learning domain, trade off floating point precision for higher throughput and efficiency, certain algorithms such as stencils, linear differential equations, as commonly found in applications such as climate modeling, still require higher precision arithmetic. Domain-specific architectures are a prominent example of how to tackle the increasing energy efficiency demands of emerging systems. Unfortunately, they are hard to adjust to algorithmic changes and frequently changing problem domains. To give a motivating example, let us consider the 64-bit application class processor called Ariane, for which we have estimated precise energy consumption and various instructions in 22 nanometers at 0.8 volt. For the fused multiply add instruction, depicted on the right, only 28 picojoule, about 37% of the instruction's energy, is spent on the actual computation. The rest is spent on instruction and data caches and auxiliary logic. Data movement and bookkeeping instruction, such as the depicted load and branch instruction, make the compute versus control energy ratio even worse. Ariane is a rather simplistic processor model, and contemporary CPUs are spending large amounts of energy on their highly out-of-order pipelines and instruction caches to keep those pipelines fed with instructions. The so-called von Neumann bottleneck is a term that describes the fact that the bandwidth of the instruction and data memory effectively limits the architectural speedup and attainable energy efficiency. Let's have a look at the trend in the industry, which paints a similar picture of the importance of increasing energy efficiency. We have picked two state-of-the-art architectures, Fujitsu's A64FX and NVIDIA's A100. Both architectures are manufactured in TSMC's 7nm process using chip-on-wafer and substrate technology. Both follow the same idea as we do with Manticore of maximizing the computational data path with respect to the control, while the A64FX uses ARM's scalable vector extension to feed wide per-core SIMD data paths with only few instructions. NVIDIA's approach in the latest Ampere architecture follows a fine-grained single-instruction multiple-thread approach to keep thousands of streaming multiprocessors and the ALUs busy. The goal for our Manticore is clear: maximize the compute control ratio as much as possible. let me introduce our Manticore multi-chiplet concept. The system consists of 4 chiplets. Each chiplet is estimated to be around 220 square millimeters in size to fit all necessary components. To obtain the most reliable estimates, we have prototyped the chiplet in a 22 nanometer process available to us. Using chiplets improves yield and cost. To allow for efficient inter-die synchronization and non-uniform memory access, each chiplet has a die-to-die short-range serial link to each of its siblings. Each chiplet comes with a private HBM2 controller and 8 GB of HBM2, as it is state-of-the-art in bandwidth and energy efficiency. Finally, each chiplet features a 16x PCI Express endpoint for host communication, as PCI Express is ubiquitous and offers relatively high-speed connections to a plethora of host devices. Let's zoom into the chiplet's architecture. The chiplet itself contains 4 quadrants, consisting of 32 clusters with 8 cores each. So one quadrant contains 256 cores, which gives a total of 1024 cores for all 4 quadrants on a chiplet. The quadrants L2 and Ariane have been placed and routed at 1 GHz as a feasibility study and to gather accurate area results. Each core contains a double precision and 2 single precision floating point units, accumulating 16 double precision and 32 single precision flop per cycle per cluster. At 1 GHz, this results in 4 tera double precision flops per second. To enhance programmability, we have included 4 Ariane manager cores, which run a general purpose operating system, such as Linux, and manage the snitch clusters and offloading to them. To balance the thermal budget and utilize the die area, we have included 27 MB of shared level 2 memory. Now let us have a closer look on the interconnect between the clusters and quadrants. Each quadrant is further subdivided into multiple levels in a tree structure using an interconnect tuned for burst-based DMA accesses. 4 clusters share an instruction cache and an uplink into the next level. These 4 clusters have a high aggregate bandwidth of 64 TB per second amongst each other and can do low latency, high bandwidth intra-cluster data transfers. As they share the uplink into the next hierarchy level, the bandwidth to the other L1 quadrants becomes smaller. Bandwidth is subsequently thinned as 4 L1 quadrants share an instruction cache and an uplink into the L2 quadrant, and 2 L2 quadrants share the uplink into the L3 quadrant. In the last level of hierarchy, 16 L3 quadrants distributed over 4 chiplets share 4 HBMs using the fully available bandwidth of the HBM of 1 TB per second. This bandwidth thinning scheme allows us to have a very low diameter, low latency interconnect topology, which can sustainably saturate the HBM bandwidth while being benign to floor planning and physical design. The interconnect allows for a very high cluster-to-cluster internal bandwidth from multiple levels, which by far exceeds the bandwidth into the memory. With this model, we can support a lot of cluster-to-cluster traffic while fully loading the memory system. Finally, we have arrived at the level of a single compute cluster. The compute cluster consists of 8 single-stage 32-bit RISC-V processor cores. Optionally, the cores can be configured for the embedded profile, with 16 instead of 32 registers. Depending on the configuration, the resulting core is between 9 and 22 kilogates in size. Each core is coupled to a large, multi-format, SIMD-capable floating point unit. The integer and floating point data paths are decoupled and execute in parallel. The aim is to maximize the area spent on floating point units compared to the area spent on the integer cores, as the floating point unit is the source of useful compute. All 8 cores have element-wise low latency access into 128 kilobytes of tightly coupled and shared scratchpad memory. Finally, a DMA engine moves large amounts of data to and from the scratchpad memory over a wide 512-bit data bus. To achieve high floating point unit utilizations, we have enhanced the integer core using 2 custom extensions: the stream semantic registers and the floating point repetition instruction. Fabian will take you through the inner workings in a minute. To give an intuition on how high we can tune the compute versus control ratio, we have analyzed the different components' area impact. The compute part, which mostly consists of floating point units, makes up for roughly 45% of the system. The shared instruction cache and control part of the core, on the other hand, just account for 12% of the cluster size. The multi-bank scratchpad memories account for the rest, which is around 44% as well. The TCDM can sustain the high bandwidth requirements exerted by the SSR ISA extension. Together with the SSRs, the TCDM can be accessed very efficiently and becomes comparable to a vector processor or GPU's register file in size and bandwidth requirements. Software can also use the TCDM memory for intercluster synchronization using RISC-V atomics and/or load reserved store conditionals. Data can be brought in and out efficiently in bulk transfers using a DMA engine and a high bandwidth interconnect network.
So how do we go about actually making the most out of the system and spending the energy where it's actually needed in the functional units like the FPUs and the ALUs? Well, our system is a RISC-V architecture, which means there's ample opportunity for custom instruction set extensions to get the most out of the hardware that we build. And there are actually two key instruction set extensions that we propose that are part of the system which allow us to make the most out of the silicon we have. The first is stream semantic registers, which is an extension of the register file, which allows us to turn register reads and writes into implicit memory loads and stores. This allows us to elide many load and store instructions which are inherent in a load store architecture like RISC-V, do them implicitly, which increases FPU and ALU utilization because these instructions otherwise would occupy an instruction fetch and decode slot, which they no longer do if they're implicit. So this allows us to increase the utilization by 3x on average for FPUs and ALUs, even up to 5x depending on the workload. And in many cases, we can get close to 100% utilization of the functional units. So for example, if you take the loop on the left, which is a classic reduction operation where you load two operands, you perform an FMA on a local accumulator register. This would require 3 cycles if you have a single issue core, one for each instruction. Now with SSRs, we can actually get rid of the 2 loads and encode them as reads from the special SSR registers. And these are just any of the registers in the register file which are given specific stream semantics. And the trade-off here is that we need some setup instructions before we enter the loop, which actually configures the address pattern. So in hardware, this is actually implemented as an extension around the core's register file. There's a subset of registers which have stream semantics, and the accesses to these registers are routed out of the core as a kind of stream access. And what we do is we actually route these accesses into an address generation unit, which sits there and assigns addresses to these register accesses. And the address generation we perform is up to 4 nested loops of affine addresses. So basically, if you have an affine loop nest that is up to 4 levels deep, we can generate the addresses for that in hardware. And it's important to understand that SSRs are not memory operands. So there's no implicit load being executed as the instruction is triggered, but it's more that we actually configure the access pattern in the hardware and we have perfect knowledge of the addresses that we're going to access, which allows us to perfectly prefetch the addresses, which makes this whole approach highly latency tolerant. So if you look at the schedule, you can actually see that the address generator can issue memory requests far ahead of the actual CPU pipeline and can actually start fetching and bringing in the operands. And as they come in, they will be put into a FIFO, and the FPU has them available when they're needed. So this is highly latency tolerant and is unlike regular memory operands. The second extension that actually makes this whole thing work is the floating point repetition buffer, which we call the FREP extension. This is basically a programmable microloop buffer, which allows us to offload inner loop bodies onto the FPU. So this is actually comprised of a custom instruction, which indicates the start of a hardware block. It's basically, for hardware loop block, it's basically a hardware loop. So this is this FREP instruction. And if you look at the loop on the left, this is the classic RISC-V loop, how you would do it without unrolling, which is an optimization you would normally do to a certain degree. You can see you increment the loop counter, you perform the actual payload, which is the fmadd, and then you have a branch instruction to actually keep iterating in the loop. And what we can do is we can replace all of this bookkeeping logic with an FREP instruction, which allows us to perform the fmadd in a hardware loop. And what happens in hardware is that if you look at how the scheme works, there's the snitch core at the top. What happens is that the instructions to the FPU, they make their way through a loop buffer, and there's an FREP sequencer on the side, which will actually step through the instructions, and in presence of FREP, will actually issue the same FMADs or any other FPU instruction multiple times. Now, what this also means is that since this is happening in the FPU, the integer core can actually operate in parallel and continue executing other instructions. We call this a pseudo-dual issue operation. And synchronization actually only happens when there's an instruction present which moves data between the FPU and the integer pipeline. And there aren't that many. The RISC-V floating point ISA is actually very well crafted in this regard, that it clearly separates the concerns of integer and floating point operations. There's only a handful of operations which actually move data between the two. And it's very easy to craft a system where the FPU runs independently for extended period of time. So let's look at the typical execution of a kernel which leverages SSRs and FREP on our cores. So the two ingredients are that SSRs enable float-only hardware loops because they get rid of load store instructions, which often means that since there's no more bookkeeping for the actual loop iteration and there's no address calculation that has to be done by the integer core, the actual loops that you need to execute become pure floating point operations. And this allows us to leverage the FREPs, which allows us to actually perform these floating point only hardware loops directly in the FPU. So let's take, for example, a reduction operation. These are very common in matrix multiplication, stem cell convolution, all the hot kernels and hot topics at the moment. We enroll it to 4 instructions to hide the latency which is involved in the floating point operations in the FMAD, as you would do in any other implementation which is tuned for performance. So let's look at this snippet of code on the left. It's basically 2 nested loops, an outer loop which iterates over elements, and an inner loop which performs the accumulation. So we have A, the accumulator, we run over n elements, and then we store the result back to memory. If we translate this to RISC-V with our instruction set extensions, it looks like the code in the middle, the following 16 instructions. So at the top, you see there's a fmove instructions which initialize the accumulator. The frep basically represents the innermost loop. We have the fmads, which represent the loop body, unrolled to 4 executions. There's an fstore, which is the write back of the instructions. And in blue at the bottom, this is the bookkeeping logic for the outermost loop. Now, these are 16 instructions. What happens now, if you look at how this executes on the actual hardware, is that the core fetches and decodes 16 instructions, but the FPU actually executes 204 instructions thanks to the frep hardware loops. And even more so, the bookkeeping operations in blue, which the integer core has to execute to actually cater to the outermost loops, these can actually happen as the FPU is still executing. So the integer core can actually overlap with the FPU, and it can do the work that is needed for the next loop iteration while the FPU is still running. This allows us to hide the setup and other overheads the integer core might impart on the kernel as the FPU is still running, which means the FPU's utilization is pushed to very high numbers. So the benefits of SSRs and FREP are manifold. So the core idea here is that the single issue core can completely saturate an FPU, which is usually not easily possible in a single issue load store instruction set architecture. This also means that we generally get an IPC which is higher than 1 because we have only few instructions that we fetch, but we execute many more because the FREPs, if you will, act as a bandwidth amplifier for instructions. Also, this greatly reduces the von Neumann bottleneck because we now have a highly reduced instruction bandwidth that the core needs to actually perform its work, because a lot of the instructions it issues only need to be fetched once and are repeated by FREP. So if you look, for example, at speedups that we see across execution on a cluster for common kernels, you can actually see that for matrix multiplication, for example, we can get more than a 5x speed up. And as you can also see, the percentages indicated, the FPU utilization goes up dramatically from 16% if we just use a baseline RISC-V implementation to 85% if we use SSR and FREP to perform this task. But also, if we look at memory-bound kernels like dot products, which don't have any data reuse, we can also see a significant gain still in these circumstances, and also a significant boost to the FPU utilization. And similarly, if we look at energy efficiency for the same sets, we can in general see that there's a significant boost to energy efficiency across all the kernels that we investigate here. This is because we now have a situation where integer and floating point pipelines can operate in pseudo-dual issue mode. So we can actually, the FPUs can continue to do meaningful work while the core runs. What this also implies is that in a single cluster, we can actually get energy efficiencies of 80 gigaflops per second and watt. And this is double precision, gigaflops per second and watt, and more than 5x speed up across workloads. But also SSRs and FREPs are applicable to less regular problems. For example, FFTs, as we indicate in the graph, but also sorting and other problems. So let's take a look at the performance roofline, which is another very interesting metric for any of these systems. So let's look at some workloads from DNN training because they're well known and they're easy to characterize. So for one, there's the compute-bound convolution. So this is if we only look at the convolution layers in a DNN training step. There are the linear pooling layers, which are generally memory-bound, and there's the mix of the kernels, which tend to be close to the convolution layers because they heavily dominate this workload. We do these estimations based on cycle-accurate hardware simulation, architectural models of a full system, but also silicon measurements of a prototype system, which we will introduce in a few steps. So generally, what we can see is that for the memory-bound kernels, we can reach more than 80% of the peak bandwidth, and for the compute-bound kernels, we can reach more than 90% of the peak performance, which is an extremely nice and close tracking of the performance roofline, which is enabled by these SSRs and FREPs, and also the combination of having a very small core attached to a very large FPU, which allows us to spend the energy where it's actually needed.
We have taped out, manufactured and measured key architectural components in a silicon prototype. The prototype has been manufactured in GlobalFoundries 22 nanometers fully depleted silicon and insulator technology with a 10 metal stack using mixed, super low and low VT flip-well standard cells. We have hardened the designs as separate macro cells and evaluated different standard cell flavors and threshold voltages. Forward body bias of the flip-well transistor design allows for trading off higher operating frequencies versus higher power consumption. On the top you can see 3 snitch clusters, each with 8 cores, which are arranged around a tightly coupled data memory in a star shape. The instruction front-end of each core is located close to the shared L1 instruction cache. The prototype also features 2 Ariane management cores in 2 different standard cell flavors, as well as 1.25 MB of L2 memory, and the first all-digital prototype of the die-to-die serial link, which is closely coupled to the pad frame. Additionally, the prototype contains various testing structures to assess silicon performance. Measurement numbers have been obtained using an industry-grade ASIC tester. Each snitch cluster has 8 KB L1 instruction cache and 128 KB TCDM, partitioned into 32 banks. The number of cores in the cluster has been set to 8, which obtains good multi-core speedups for the various microbenchmarks we have run. Furthermore, an 8-core configuration is suitable to be hardened as a standalone macro block, as it is not too small or too big. The 2 Ariane cores come with 16 and 32 KB L1 instruction and data cache. Furthermore, we also provisioned an 8 KB scratch-read memory as a fast memory in the core's clock domain. One additional snitch management core is used as a governor for testing, power management, as well as DVFS tasks. The all-digital serial link operates at 400 MHz using double data rate with a lightweight credit-based encoding scheme. Being all digital, the link can be comfortably ported between technologies and allows for an easier bring-up. The chip additionally contains 4 FLLs used for frequency synthesis of the 2 Ariane cores, the snitch clusters, peripherals, and the top level.
So let's look at how our silicon actually performs and how the efficiency hold up. So as we can see, when we actually run kernels on the actual silicon and we do measurements, we get 90% and above 90% FPU utilization thanks to the snitch cores with FREP and SSRs. But also we get a very wide range of operating points, and there's a nice set of choice for performance efficiency trade-offs across the board. So on the prototype silicon, we can get up to 54 gigaflops per second across 24 cores, and that's double precision gigaflops per second. And if you extrapolate this to the full Manticore system, this is more than 27 double precision teraflops per second across the 4,000 cores that we propose. And both of these numbers are in 22 nanometers, so in GlobalFoundries 22 FTX. There's still a lot of tech gain to be had if we move to smaller technologies. Also, the compute efficiency can go up to 188 gigaflops per second and watt, again, double precision gigaflops per second and watt. And the compute density goes up to 20 gigaflops per second and square millimeters. Regarding power and speed of the silicon, as we already said, the silicon supports a wide power and frequency envelope. And we can leverage dynamic voltage and frequency scaling based on the operational intensity of the current workload, for example, to actually position ourselves on this trade-off graph and get the most out of the silicon while still meeting the performance requirements that the current workload has. So what this allows us to do is actually we can adjust the roofline of our system to match the workload. So the workload always sits in this ridge point. So if we look at the extreme high performance mode, for example, where we get 54 gigaflops per second, this is at 0.9 volts and at more than a gigahertz of sustained compute in this system. But also, if that's not required, we can actually go into a high efficiency mode where we get more than 188 gigaflops per second and watt at 0.6 volts of supply, but still at 500 megahertz of sustained compute. So there's a wide range of efficiencies and performances to be had while still maintaining reasonable compute throughput even in the high efficiency corner. So let's look at the efficiency on floating point operations, more specifically on 64-bit double precision operations. Our system can actually achieve industry-leading 64-bit floating point efficiencies if we compare it to other systems and we assume that 90% of their peak performance that is generally stated by the vendors is actually sustainable for actual computation and workloads. We can actually make a few comparisons with our system. And what we see is that if we run in maximum efficiency mode, we can actually outperform an Intel i9 core by 15x in terms of energy efficiency. Celerity, which is another RISC-V based architecture, by 9x, 7x compared to the Neoverse N1, 6x compared to the NVIDIA Volta. And if we extrapolate from the preliminary results that we have from the Ampere white papers, also 5x compared to the A100. And if we're not so interested in energy efficiency, but we want maximum performance, we can switch the system into maximum performance mode. And in that case, it is competitive in terms of energy efficiency, still with the Neoverse N1, the Volta V100, or preliminarily also with the Ampere A100. And if we take a look at 32-bit floating point, that is single precision floating point operations, we can actually see that our system has a competitive efficiency in this realm. So if we again assume that competing systems can achieve 90% of the peak performance, and that is sustainable for computational workloads, we can actually look more towards the field of DNN training as an interesting workload. We can again compare convolution-only part of the workload, which is heavily compute-bound, and also a full layer mix of memory-bound kernels mixed in between. And what we can see here is that we're actually competitive with the V100 in this setting, which is highly tuned to perform well on these kinds of workloads and has seen a lot of optimization in this regard. And we can still outperform an i9 by 2x in terms of energy efficiency and the Neoverse N1 by 3x, again in terms of energy efficiency. Compared to the Ampere A100, we expect to be roughly 25% lower in efficiency, which is mainly due to a very, very big technological gap between our 22 nanometer results and estimates and the Ampere's cutting-edge 7 nanometer technology that it runs on. So to wrap things up, we've actually shown in this system that we can combine a very small integer core with a very large FPU and have the small core be sufficient to actually sustain compute on the FPU. The key takeaway point here is that this allows us to actually keep all the bookkeeping logic small and keep the FPU very large, which allows us to spend all the energy in the system on the FPUs where it's actually contributing to the result, if you will. The key thing that allows us to do is the two instruction set extensions that we've proposed, the SSRs and the FREPs, which also along the way help to combat the von Neumann bottleneck and reduce the instruction fetch bandwidth. And it allows a small single issue in order core to fully sustain compute on an FPU without an inherent architectural limit to the utilization that you can achieve. So we can get very close to 100% across a very large range of kernels. We've shown that with such a setup and such a system, we can achieve extreme energy efficiencies for double precision floating point operation, and we can be highly competitive for 32-bit floating point operations, and that all on a 22 nanometer process, so not even the most recent cutting edge technologies, which would give even more benefits. So in the future, what we're planning to do is we have a quad chiplet prototype board, which combines 4 dies of the prototype silicon that we've constructed to test out various communication, the serial links, and generally arranging these things into a chiplet. And the next steps are to bring this up and actually show computation on that and how this can be leveraged to crunch the problems of today and tomorrow. Also, we're pushing towards manufacturing a larger silicon prototype in FinFET technology, where we can actually see the effects of going to a more aggressively scaled technology, which gives us even more energy efficiency benefits and other trade-offs. In general, we're looking for industrial partners for die-to-die link, HBM, and DDR-PHY integration, and also to collaborate on pushing towards these more aggressively scaled technologies to show the benefits of our technology and of this approach to large-scale computation to tackle today's computationally intensive problems. So with that, I would like to close and thank you all for attending our talk on the Manticore architecture. Thanks for listening in, and we're very much looking forward to your questions and feedback. Thank you.
Guys, thanks very much. Great talk, and thanks for joining so late in Zurich. We're a bit over time, so I'll just pick 2 questions for you. The first one is, how does the compiler target the new instructions that you define?
So the main approach we envision to take there, so on the one hand, the compiler can actually take advantage of this automatically because there's transformations that you can do in detecting the loops inside your code, which allows you to automatically promote loop bodies which have the necessary characteristics of having only floating point operations, etc., and actually promote them to SSR and FREP capable loops. That works in a kind of general approach, but this needs more exploration, and it might also not hit all the cases that you're interested in. So a second approach is to kind of go the QDNN road, where you would provide a highly optimized implementation of basically low-level kernels that are composable on a higher level via frameworks like TensorFlow, PyTorch, NumPy, whatever you have.
All right, thank you. And one more question. Do you have any plans of productizing this?
Yeah, so right now this is a concept, and we have manufactured this prototype to explore the key architectural components. And what we wanted to try out was to have very lean but mean RISC-V cores tuned for maximum efficiency. And what we are still missing are these key components in the SoC level, high-speed interconnects, which we just don't come by as a university very easily. So I think productization is quite a bit in the future, but we are looking into generating and taping out larger systems in still prototype and research kind of system in the future.
All right. Florian, Fabian, thanks. Great work.
Thanks for having us.
Thank
All
you
right,
very much.
folks, this concludes our machine learning training session.